According to the National Automobile Dealers Association, the mean price for used cars is at least $10,192. A manager of a Kansas City used car dealership reviewed a sample of 100 recent used car sales. The sample mean was $9,300, where the population standard deviation was assumed known at $4,500. This estimate of the population standard deviation was taken from this sample along with several others, so they felt that they had a very good estimate of the population value, and is assuming then that the standard deviation is known in this problem. Use the sample to test the National Automobile Dealer Association's claim. Let alpha be 0.05. Interpret the results. Well, the Dealers Association is claiming that the mean price for used cars is at least $10,000, and we're asked to test that. So that this is a hypothesis test, and it is a hypothesis test concerning averages. So I need to set up a null and alternative hypothesis, and we're testing a claim in this one. We're testing to see if we have a strong enough evidence from this sample to say that the Automobile Dealers Association claim of at least $10,192 to see if we have enough evidence to show that's not correct. But what we will do is assume that what their claim is correct. And so they said at least, so we're going to assume that the population average is at least the $10,192. And notice that our sample average is 9,300. So we really have some evidence that it may not be at least 10,192. And we're going to see if that's strong enough evidence, though, to reject the null hypothesis and show that the average is 10,192 or is less than that. Okay, the first step of a hypothesis test is to set up the null and alternative hypothesis. The next thing I need to do is to build my sampling distribution, and I have a good estimate of sigma, so good that they're pretty much saying we have the population standard deviation at 4,500. So with a sample size of 100, I'm good to go with a standard normal distribution. So I'm going to say sigma sub x bar, my standard error for this would be the 4,500, and then divided by the square root of the sample size. Our sample was 100, so we get a standard error of 450. We're going to assume that the null hypothesis is correct for now and say that the average, the population average, is the 10,192. Our sample average at 9,300 is evidence that the population average might be less than that 10,192. We're going to test on the lower end and set up our level of significance at 0.05. So with standard normal distribution, that would give us a critical value of negative 1.645 down there on the lower end. A lot of times we'll think of that as my second step, kind of bringing the information together and looking at the sampling distribution. That's assuming that the null hypothesis is correct. My step 3 then would be to create a rejection rule. So I'm going to reject H sub 0 if my test statistic Z is less than the negative 1.645. And the test statistic I'd be talking about in this problem is the Z value for the 9,300. I'm trying to figure out how far the 9,300 is from the claimed 10,192 what the difference is in standard units. How many standard deviations are there between those two values? And then calculating that, I would get a negative 1.98. So that is to the left of my critical value, my decision line there. And therefore, I'm far enough away from the claimed 10,192 that I'm willing to take the risk and reject H sub 0 and say or conclude that the mean price for used cars is less than the $10,192. So I have evidence here to show that their claim is incorrect. Now let's go ahead and talk about the p-value. Type 1 error is rejecting the null hypothesis when the null hypothesis is, in reality, true. When we set alpha equal to 5%, we are saying that we want no more than a 5% probability of making a type 1 error. So, in step 2, we set up the sampling distribution, assuming that H sub 0 is true. We draw our decision line at the z location, negative 1.645. If H sub 0 is true, only 5% of the sample averages that we would get from sampling of size 100 are to the left of this line. 95% of the sample averages are above this line. If H sub 0 were true, there is a 95% chance of getting values to the right of this line and a 5% chance of getting values to the left. So when we get a sample average to the left, it sheds enough doubt on H sub 0 that we are willing to reject it. Now it is possible to get a sample average to the left of the line while H sub 0 is true, but there is only 5% chance of that happening. 5%, the level of significance, is the risk we are willing to take when we reject the null hypothesis. The p-value method helps us express the strength of our evidence. It answers the question, what is the probability that we would observe our particular sample mean if in fact the null hypothesis was true? To calculate the p-value, I'm going to look at the test statistic for our 9,300 sample mean, and it is negative 1.98. The negative 1.98 is to the left of negative 1.645, indicating that the 9,300 was further out than it had to be for the rejection. Now, to determine then the strength of that evidence, I want to go ahead and calculate the p-value. So the probability of getting anything less likely than the 9,300 is going to be calculated by finding the area under the density function below the 9,300, or from the table to the left of the negative 1.98, and that is 0.0239. So 0.0239 is less than the maximum allowable risk that we were willing to take, and therefore we reject h sub 0 as before. Approaching the test using a p-value is nice, and it is very commonly used because it not only determines whether we can reject the null hypothesis or not, but it gives us a feeling of the strength of our evidence. The 9,300 sample mean was really further out than it had to be under our 5% risk. So with the 0.0239, it gives you a feeling of how much further it was out there, and that the evidence was even stronger than it had to be. Also notice that in a problem like this, that whether you use the test statistic critical value approach as we did at first, or comparing the p-value to the level of significance, these will always agree. It's really just two different methods that are closely related.